Thanks, guys, for having me here today. There's a lot of you, a lot more than when I used to be the TA for this class back in '97. So I actually know what you're going through. I know the pain you have with the sponsors. And actually, maybe I know the pain better than you guys do because you haven't even hit the pain yet. At some point, the sponsor will ask you to do something unreasonable, and you'll like have this welling up of pride inside of you that says, "I can get it done. I can work the weekends. I can make these guys happy." And Judy will come back to you and say, that isn't the point of this. The point of this is to recognize that sometimes they will ask you to do unreasonable things with schedules that are unreasonable, and that's part of the learning process here. Anyway, so today we're going to talk about, like Judy said, her area of specialty, and I'm delighted that she asked me to come in and chat with you guys. One of the things that that I think I can do somewhat better than most of the people in my position that get up in front of people and go blah, blah, blah about software architecture is that I've actually done a lot of this stuff myself. Okay, so there's people that are on the academic track and they go straight through, and maybe you guys are planning next year to go to grad school, right? In which case you've done a little bit of dallying here and there with projects, but it's not like you were in the trenches for 10 years. Okay, so roughly I was in the trenches for 10 years and I went back and got a PhD, and now I do a little bit mixture of both. So hopefully that some of this stuff is fairly well grounded. As a way of establishing the fact that I'm real and I've got street cred, I have like 6 boxes running Linux in my house right now, okay? 2 of which are on all the time. How many people here run Linux? Yes, I can't believe that. That's fantastic. Okay, so glad to hear it. It's not that Linux is necessarily the best thing in the world, but if you're trying to learn about software development, it's very easy to get under the covers and make a lot of things happen where it's harder in other places. What I'm going to talk to you guys about here for the next 3 hours or something like that is really difficult to talk to people about if you hadn't already had the experience. Because a lot of times you have to have had 2 or 3 times where you've seen that same thing happen, and then you can recognize the pattern of what's going on. So we're going to try it the way we usually do in undergraduate education. So we're going to tell you about it in advance. And then hopefully, 2 years later, when you remember 1% of this lecture, you'll have some glimmering memory that maybe this stuff will be applicable. That kind of thing happened to me over and over again when it came to like finite state machines. And eventually you go, I'm 25 years old and I'm practicing programmer. I'm like, oh wait, this is a finite state machine problem, right? Or this is a parsing problem. And it's just like you go, oh yes, I need to go back and pick up the formalism so that I can make some progress. Okay, so without further ado, let's talk about something concrete. A tale of 2 systems. So you guys all use Skype, probably use Skype more than you use telephones. But the standard old telephone network, roughly speaking, does exactly the same thing as Skype does. From a feature standpoint, you can call somebody else who's in the network, where in the network can mean you have a physical telephone hooked up, or in the network can mean you have Skype running on your computer. And you'll notice that they have pretty different architectures. Have you ever seen, this is one of these things that you don't notice until you've been clued into it. There are buildings in large cities that have no windows. Have you seen those before? Yeah. These days, sometimes those are actually server buildings, right? But in the old days, those were exclusively owned by AT&T, right? That's where they hardened the building. They didn't put any windows on it. It had to be brick according to code. And this is where all these cable bundles would come in from all around the city. And we're talking cable bundles that end up being bigger than you can get your arms around. Just big cable bundles of copper stuff coming into a centralized hardware switch. Now let's compare that with the architecture of what Skype does. Skype really runs on every one of your computers. And there's a little asterisk here that says there are a handful of Skype master servers, right? These super nodes. But let's forget about those for the minute. For the time being, let's just talk about it as being peer-to-peer. Now, the interesting qualities of the plain old telephone system, also called POTS, is that it works during power outages. Anybody know why that works? How can that work? How can it work when the power's off? But have you ever had that happen? Your phone works, but the power's out in the house? Probably no one here has a plain old telephone.
I don't think those exist anymore.
They do. I've got one, I promise.
Days.
Yeah, I'm the only one. So as it turns out, they put voltage on the wire. They put voltage. They have these big, massive battery, another big room full of batteries, so that they can make sure they put power on the wire even if the telephone lines get cut. And the reason for this was they wanted to make sure it was reliable. So there's things that you can do that seem crazy, but you can actually get to that reliability. And emergency calls can get your location information, obviously, because you're not moving the physical wire. Now, the good qualities of Skype are that it scales without any central hardware changes, and it was really easy to add new features like video calling, right? For the longest time, people talked about video calling with regular phones, and it never really arrived. But when it comes to Skype, it's like we got it and we got it for free, which is kind of amazing. And it's mostly due to the fact that they have a different kind of architecture. If your computer is fast enough to decode the video, compress it and decompress it, well, then it can shoot it across the wire just the same way it does voice. So if you remember nothing else from this lecture, I want you to remember one thing, and that's at the bottom of the slide here. Architects pay more attention to qualities that arise from the architecture choices. There are two architecture choices we were seeing here. One is a centralized hardware switch, and another one is peer-to-peer software. You can make phone calls happen with either architecture. But if you were to try to make Skype as reliable as the plain old telephone system, you're probably never going to get there because you can't put voltage on Wi-Fi, right? It's just never going to work out. If your laptop's dead, your laptop's dead. On the other hand, over here, with the plain old telephone system, you're going to have a really hard time adding certain kinds of features just because of the choices you've made regarding reliability. So you're forced with this trade-off. Okay? So let's actually design a system ourselves. And let's imagine that you're a hosting provider, right? You're like Amazon EC2 or somebody else. And what you're going to do is you rent out mail servers. Your customers are going to have problems, so invariably they're going to call you up and say, what's going on? The mail is not getting delivered. So what you got to do is you got to dig into log files to figure out what's going on. So here's your question. How would you build this thing? You've got a lot of choices, and we know that different architectures can yield different qualities. So what do you guys want to do? Anyone want to yell out a suggestion? And if you don't start talking, I'll pick on you. Yep.
Get a server farm, virtualize out SMTP servers.
Okay. And how do I solve my problem, which is people are going to call in and ask me to diagnose problems?
Hire out, or what is it called? Outsource it?
Well, you're the outsourcing company. That's a good answer, but I'm going to ask you to design it. You're the guy who's engineering this. So, yeah.
Centralize the log server.
Okay. So I've got a lot of different mail servers, but I'm going to send all the logs to one place?
Right.
Okay, great. And then how do I, when someone calls up, what do I do?
Then you can easily search the one server because you've got them all right in one place.
Okay, and I'm just going to ask you to be even more specific. So specifically, how would you search that server? I mean, how would you store the logs on that server so they were easy or hard to search?
Well, you could put them in a database. That
Okay.
would be a lot quicker for you. You could use flat files if
Yep.
you really wanted to and use grep or something like that to do searching for you.
That's really interesting. Why would you choose one of those versus the other one?
Well, I don't know. Flat files you don't have to worry about. I guess if you have some sort of redundancy for your hard disk or something that using RAID 5, RAID 6, you would be able to potentially have multiple log files being written to at the same time, but it's writing to the same database.
Actually, let me back up for a second, just to make sure we're all on the same page here. The two alternatives that have been discussed. Well, the first, the idea was, there's lots of mail servers and they have logs. Send all those logs to one server, okay? So far, so good. And then there were two options on the server. One is just leave it as a big pile of log files, right? A bunch of files sitting in a directory. And the other was take those files and put them into a relational database. And I'm assuming something here. I think what you mean is you want it into an indexed relational database, right? You want to have an index that makes it faster to do the searching, okay? And what that means is when you put it into the database, it's going to do indexing right up front. Otherwise, it wouldn't be any faster to search, right? So my two alternatives for searching are, when someone asks me to search, I start at the beginning of the first file and start cruising through until I get to the end of the last file, right? Looking for Bob Smith and looking for an error message, okay? The other alternative is I can index in advance, but I have to pay that price up front. I have to pay the price while I'm streaming the log files in, and then searching becomes quicker.
You have like a dedicated log server, so you don't really have to worry about that. It just has that one task, the overhead doesn't really matter.
Okay, so what you're suggesting is if I get a nice beefy log server, if I stream the stuff in, I'm not paying much cost about getting them indexed in advance. Okay, so let's take a look at you guys are doing a great job with that. Let's look at the right-hand side. This becomes hard when the number of servers you have increases to some unreasonable number. Maybe hundreds is not unreasonable, but certainly thousands would start to be difficult. You generate gigabytes of logs daily, which just means you're trying to use your network to actually run your business, but you end up using your network just streaming log files around, okay? Collecting the log files takes time, searching the log files takes time, indexing the log files takes time. But you guys are the architects, you're the designers of this system. You need to make this choice up front, which one you're going to do. So Some of the things you guys pointed out here, you could have central collection of the logs, or they could be distributed. And you could pre-process the logs to figure out if you could speed up the queries. Okay? Because if you had a lot of logs and somebody calls up and says, hey, I'm Bob Smith, I've got a problem, and you've got a lot of logs, it could take a long time before you could answer their question. Okay, so here's the interesting bit. This actually happened to a company you probably have heard of, Rackspace. You guys have heard of Rackspace before? I think it's like the second biggest hosting provider. Amazon's the biggest and Rackspace is the second biggest. So they had exactly this experience. And they experienced huge growth in the number of mail servers they had. And they went through a progression of 3 different systems that did exactly the same thing we're talking about, but these 3 different architectures. This almost never happens, and so it's like a wonderful dream for somebody who wants to study how systems work, what the impact of the architecture is. So it lets us take a look at those 3 systems and see how the architecture impacts the qualities you get out and the sort of trade-offs you have to make. Okay? So let's take a look at the 3. The first one was you've got mail servers, they've got local disk with log files on them, and they wrote a couple of scripts so that when Bob Smith calls up, you would execute some grep, as you guys suggested, and it would actually send the grep out to each one of the machines, and so in parallel it would grep all the log files. And the problem with this is what they found out is as they started to grow and the number of queries starts to come in, if you've got one server, let's say you've got 10 clients, right, 10 users. Well, you've got 2 servers, you've got 20 users. As this thing starts to scale up, you've got a lot of users and it becomes more and more frequent that one of them is calling up to ask you a question. But the problem is you have to search every single server every single time you have, have somebody call up. So what they found is that pretty quickly their servers, which started out with a negligible amount of load for searching the log files, started spending 20–30% of their time searching the log files instead of actually serving mail. And they said, look, we got to figure out something better. So they did exactly what was suggested. They centralized the log files. They put them in a MySQL database. So now they have the data being logged initially out of the mail servers, but periodically they push the log files up to MySQL. And as a result, MySQL can index things. So when Bob Smith calls up and says, I've got a mail problem, it looks in the index in MySQL and gets the answer back a lot quicker. So what do you think could possibly go wrong with this?
MySQL can become overloaded.
Exactly so. So first of all, it takes a lot of load to get all these files into the server. You want to be able to do a switchover where you say, I've got all these new files, I want to add them into the index. That actually was a tricky bit for them to do. And then finally, what they were doing was what's called a scale-up strategy. They kept getting a bigger box with more RAM and more CPUs and more disks, as opposed to saying a scale-out strategy, which is we've got a bunch of little boxes that share the load. So what they found was, and you can argue about whether they were using it correctly, but what they found was that they couldn't get that box to be reliable enough under the amount of load that they were putting on it, okay? And there was no option to buy a bigger box, or at least not within reason. So what they did was they went with architecture number 3, which is that they streamed data into a distributed file system. So what we're talking about is a bunch of commodity boxes just with the regular disks in it. And then periodically, I think every 15 minutes or so, they would run a MapReduce job. And the MapReduce job would index all the files that were there. So the idea is they had sort of the same functionalities they had with MySQL and the indexes, so you get fast searches. But you also had the advantage that this thing scales horizontally instead of vertically, such that if they need more capacity, they just add more boxes to it. Okay? Do those 3 options make sense to everybody, why they proceeded this way? Okay. So one thing to notice here is that they had to make engineering trade-offs. It's not like they went from a bad system to a better system to a good system. It's instead they had a system that had certain qualities, pros and cons, for each step along the way. So in the first one, you'll notice that the queries run on the current set of data. So if somebody calls up and says, 2 seconds ago I just got an error from my server, I can search through the logs and I should be able to find that error. In the second system, where we put it into MySQL, you would have to wait at least 10 minutes before that error message made its way into MySQL, and then maybe even wait for the indexing to happen. So you've got some latency before you can start to see the errors. So you can't diagnose errors in real time. Okay? And then with a third one, you had the same sort of thing going on, that you were pushing data up into this distributed file system, and then you're running a job that would index through everything. So you've got even more latency. The second one is scalability. Notice that the first one we ran out of scalability fairly quickly. The second one, it worked for quite a while, up to about hundreds of servers, and then it fell over. And then with the third one, they claim they have no problems yet, right? That they continue to be able to scale up. And then the last one is in terms of the, how long does it take me to write a brand new query that I want to do? With the first one, they were just writing regular expressions. And now, granted, you have to learn regular expressions. But once you know how to do it, you can just type that in and grep will run it for you. In the second one, you had an SQL expression, which, again, is fairly easy. It's meant to be used by non-computer science majors. But in the third one, even though they claim that MapReduce programs are not all that hard to write, you still have to fire up Java, and you got to write a MapReduce program, and you got to test it and hope it's giving you the thing that you're expecting to get. So you start looking much more like a software developer in order to do these things. Okay, so what was the number one point that I wanted you guys to remember at the end of this lecture? You forgot already. There's no hope for you. Come on. That's the correlate, exactly, right? So the idea is that for any given functionality, like we want to build a mail server, there's a bunch of different architectures we could use, and we're going to end up with trade-offs. And architects are going to pay attention to the qualities that are promoted or inhibited. So when you look at these three systems, I don't want you to think the answer to all of our questions is always to use Hadoop and MapReduce, right? Because that's not always the right answer to your question. Notice that what you're losing is you lose data freshness, you get scalability, and you suddenly now have to have software developers that write your queries for you, right? It's not necessarily a win for this company, okay? In this case, probably on balance is the best one, but the point is they did have trade-offs. This is a horribly boring slide, but I feel compelled to actually say, what is software architecture? And the definition at the top is clearly my favorite because it says what's in and what's out. If you guys ever heard the definition of software architecture is it's the things that are hard to change later. You guys heard that before? It's actually a very compelling definition. In some ways, I really like it. But the problem with it is it doesn't say what's in and what's out. So for example, my boss is really hard to change later. It's hard to argue that my boss is architectural, okay? There's any number of things that are difficult on the project that are hard to change later, like the seating arrangement of the software developers might be something that if you rent this office space, it's hard to change. But that's not something that's about the architecture of the system, okay? So in loose language, I'm going to call it's the big picture or macroscopic organization of the system and how it influences the qualities of the system. So the best way to think about this is that every system is going to have an architecture. There's no such thing as a software system without an architecture. But it's not necessarily the case that the architecture for the system helps it do what it wants to do, okay? So in the first example, we talked about a telephone system, and you could use a peer-to-peer architecture where everyone's an equal node in the network, or another one where you centralize everything, okay? Can you think of another kind of software system you've ever seen in the world? Just give me another example, and let's see if we can figure out how we would make a telephone system out of it. Okay, let's just say, does anyone know of any other kinds of architecture besides peer-to-peer and centralized server?
Distributed servers?
Sorry?
Like distributed servers? Where instead of having one centralized server, you have another.
Right, okay, yeah, that would work. So you centralize servers, but there's a whole bunch of them instead of one big one. Okay. I don't think we're going to see a whole lot of difference in this example from that one. How about your operating system on your computer? How does that work? It is local, yeah. Those of you that run Linux, what are daemons? They're little server processes that do very small jobs. And do they run in the same address space, or do they run in separate processes? They all run in separate processes, right? And the reason for that is if one of them crashes, what happens to the rest of the operating system? Keeps going, right? And that's the number one thing with an operating system. You don't want to have the situation where you crash the whole operating system because you made one programming error, okay? So let's think about that architecture for a second. Is that appropriate for building a telephone network? Well, no, because it all runs on one computer, right? It just stops making any sense. But somehow you can imagine running a telephone network on your computer, but you'd only be able to talk to yourself, whatever that means, right? You could have one program talk to the other program. Okay, so the idea is that the system is going to have different kinds of requirements, quality requirements like performance, security, availability, reliability, and you have functional needs like I need to be able to make a phone call from one place to another. And generally what you're going to try and do is you're going to try and line those things up so that the requirements you've got, both functionality and qualities, are fairly compatible with the architecture you've chosen, with fully understanding that you don't know how the future is going to unfold. Just like Rackspace, they didn't know how the future was going to unfold. You got to imagine that they were rational all the way through. And since it's hard to change the architecture later, it's worthwhile thinking about it at the beginning. And I want to make sure you guys understand, this does not mean BDUF, big design up front. This doesn't mean you spend the first 3 months of the project doing the architecture. But what it does mean is that if you don't pay attention to this stuff, you're probably just going to choose an architecture by default and not necessarily one that's going to be suitable for your program. So there's a reason that there's a horse on this picture, and I'm going to tell you a little story. I'm going to ask you to choose between humans and horses as the 2 different architectures, or 4 legs or 2 legs. So imagine I gave you the functionality that says, you're a farmer and you need to move apples from your farm to the market. And I'm going to ask you to choose an architecture, i.e. horses or people. Which one do you think is most suitable for this job?
People.
Hmm?
People.
Ah, very interesting. Why do you say that?
Because the best thing I can see a horse doing is 1 apple at a time in his mouth.
Ah, well, let's imagine we had a horse and we could put a bag on it, put saddlebags on him, or you can pull a cart or something.
How's he going to get the apples in the bag?
So again, this is perfect, okay? Because normally people would say, absolutely, you want the horse because the horse can take, bushels and bushels of apples, whereas one guy carrying a bushel of apples is about all he can do, okay? And what you want to do is you say, well, imagine you get to the market and I change the requirements and I say, well, yesterday I just asked you to move the apples, but now I want you to place the apples on the shelf. Well, suddenly the people look a lot more compelling as an option, or a horse plus a person. So what I'm just trying to say here is you'd like to choose your architecture up front. It's going to be hard to change later once you've chosen, but you have to be somewhat willing to understand that you're not going to choose correctly. You might have to change later, just like Rackspace did. Okay, so this is supposed to be the scary slide. I don't think I'm going to do any good job at scaring you guys. But what happens if you don't think about architecture? What happens if you just sort of think from the bottom up and say, I know these technologies, I can eventually glue them together? Well, first thing that happens is you end up with local optimizations that make sense, for example, for your part of the project, but that don't make sense for the project as a whole. This is the part where I would usually say, hey, have you guys ever been on a project where one of your coworkers made some little bit run extremely fast, but then it turns out no one could interoperate with this stuff because he, I don't know, denormalized the data structures or something like that. And you go, oh yeah, that's happened to me. But unfortunately, fortunately, because you're, how old are you guys? 21 years old? 22? No? Good. 21?
25.
25? Excellent. So you've seen this before?
No.
Okay. So one thing you will be irritated by is there'll be some people that can just sort of seem to automatically choose the right thing, and their designs always work out. Maybe like Jeff Dean or James Gosling, if you know who these guys are. Hoping that you're going to be James Gosling or Jeff Dean is like sticking your head in a bucket of paint. I mean, it's not going to help you out hoping you're this person. You're either this person or you're not. And even these guys are going to be aided by understanding how to think about architecture. If you don't think architecturally, you're going to have lousy communication with your coworkers. Can anyone tell me the difference between a process and a thread? Have you guys all taken operating systems at this point? Okay, good. So then everyone knows the answer to this question. So anyone, tell me the difference between a process and a thread.
Shared memory versus not shared.
Say again?
Shared memory versus not shared.
So which is which?
Threads have shared memory. They also step all over each other, which makes it difficult, but they also have...
A+, you're the only one in the class that passes. No. So yeah, so the reason that this is important, it's not because I care about operating systems right now. It's the point is, if you have 2 guys who work on operating systems, and one guy starts talking about threads, but he really means processes, the other guy's gonna be smacking him around saying, you don't know what you're talking about, right? There's actual terminology they can use to communicate with each other. Can anyone tell me the difference between a component and a module? Judy can tell me the difference between a component and a module because we're in the same field. We're in the field of architecture, and these words have meaning just the same way that threads and processes do. And if somebody starts coming in here talking about modules and they're really talking about components, I'll be like, come on, go back, learn your technology before we can talk. Actually, I don't do that. I usually have to teach them what's going on. The next thing is you end up with shallow analysis of your design options. What you end up with is some guy comes in and says, hey, I think we can do it this way. But he's really suggested some way that's based upon his past history rather than actually understanding what his options are. And standard patterns of architecture are ignored. So when I asked you guys a few minutes ago, what are the standard architectural patterns? And we already knew about centralized server, and we knew about peer-to-peer, and it took a while for us to get to any other ones. Well, it turns out there's like a dozen of these things, and it'd be really great to know what each one of them is good for, rather than sort of wandering into it. It's nice to know up front. So that was sort of the bad news slide. Here's the good news slide. Can anyone here do algebra? Yes, algebra. When did you learn algebra, roughly? Like 3 plus x equals 5. When did you learn how to do that?
Grade school.
Okay, and can you guys do calculus? When did you learn calculus? Sometime in high school, okay? Now, you're willing to believe me that at some point, the vast majority of students did not know algebra, right? And you're willing to believe me that at some point, only a handful of people understood calculus, okay? It really took the virtuosos to get to that level of competence. And so what we do as a field is we figure out how to compress that knowledge and teach people younger. And why do we possibly want to do that? Because I'm sure all of you guys had a delightful time in algebra and in calculus, okay? And I promise it's not to make your life difficult in high school. Instead, the idea is that the one thing that's unchanging from generation to generation is that we've only got 80 years on the planet, okay? And so you might imagine, if I have to learn everything that my father did during his lifetime, well, then I can't really learn anything new. I could just learn different stuff. But if I can compress what my father knew and learn it a little bit faster than he learned it, well, then suddenly I can do extra things. I can go farther than he was before. So you've heard this expression about standing on the shoulders of giants. It's not so much standing on the shoulders of giants as shrinking that body of knowledge down to a digestible chunk such that you can learn it as a declarative unit, right? The standard patterns of software architecture are A, B, C, D, E, right? Just the same way that you learned, if you're doing differential equations, they're these standard patterns of how to do the work, right? So since we've been able to do that, we can compress the knowledge down. And as a result, every civil engineer today is better than any of the Roman engineers in existence, right? Roman being ancient Romans, right? So if you come in and say, I just built a new viaduct between Longmont and Lyons, it's not going to make the paper, right? Because everyone knows how to move water around from city to city. But when the Romans did it, it was a big deal. 5 years ago or so, if you had built a highly scalable distributed system based on commodity hardware, I would say you were probably in the San Francisco Bay Area, right? Because there was a community of knowledge that people knew how to do this. Maybe make that number 7 years ago. It was not in books. It was not discussed on websites. For the most part, you weren't allowed to talk about it over dinner because it was still proprietary stuff. Maybe about 3 or 4 years ago, this stuff was talked about at conferences and became fairly well known. And today, there's any number of open source projects that just show people how to do this stuff, right? From soup to nuts. It tells you, here's how you do the load balancing, here's how you do the distributed file systems, here's how you do the distributed processing, here's the pros and cons of doing all the different options, okay? So what's happening is it went from being this craft that only a few people in the know knew how to do to being a commoditized thing that any one of you guys could pick up and learn. And what's going to happen is over your lifetimes, you're going to take that for granted the same way in the 1970s when they invented relational databases, people had to really work about getting their database structures right. Now we take for granted we can get anything off the shelf and work with it from there. So we can teach software architecture. We're actually getting pretty good at it. And it's sort of a shame that you guys don't have an undergraduate course on software architecture because it could really help you out. Think about this. When you go to take a compilers class or take an operating systems class, compilers and operating systems use 2 different architectural styles, right? If you build a compiler like you build an operating system with a bunch of daemons that run, that would be kind of silly, right? Having an architecture course before you went into that would help you understand why they chose the architectures that they did for those kinds of systems. Okay. We have now entered the main bulk of the lecture. Does anyone want to stand up and stretch? And no? You guys are troopers. 3 hours straight. No breaks, no water. Okay, just teasing. Okay, so here's what we're going to do. Like I said, it is possible to teach software architecture. This is going to feel a bit like drinking from a fire hose. And honestly, I don't expect that in a couple weeks you're going to retain a lot of this stuff, just because that's just the way these things go. Unless you apply this knowledge, it's going to drip out. So these are the topics we're going to talk about. The first one is the relationship between architecture, the process of architecting, and the people who are architects. We're going to talk about using views to look at systems so that you can understand a subset of the system and solve the problems you've got. We're going to talk about quality attributes like performance, scalability, reliability separately from features. We're going to talk about how you can analyze architectures to find out if they're going to do what you expect them to do. We're going to talk about standard notations. Guide rails is an idea that you deliberately constrain yourself so that the system does what you would expect it to do. We're going to talk about some of the standard architectural styles. We're going to talk about a conceptual model for how you think about architecture. Engineering with models, which means like if you ever did one of those two trains are traveling at each other, you're taking a story problem and you turn it into algebra, and then you map it back to the real world and say the trains will meet each other in 5 minutes. We're going to do the same sort of thing with software. We're going to talk about the standard structure for software architecture. We're going to talk about how models and code are different than each other and how that can get you in trouble. And then finally, we're going to talk a little bit about how much architecture you should do, because you don't have an infinite amount of time to get all this stuff done. Okay? Make sense? Oh my God. Put on your seatbelt, get ready. All right. This is a big deal, this difference between architecture, architecting, and the architect, because people mix the three things up. Some people will reject the idea of architecture because they think it's just a fluffy sounding title. Have you guys ever heard of sanitation engineering? Yeah, people just call that trash collection, right? So they just put engineering on the end of anything they want to sound better. And I've noticed a similar trend now that software architecture has become more of a big deal. People put architect in their title just so it sounds like a bigger deal. And it generally happens, I'm speaking cynically here, it generally happens to people after they've been with a company for a long period of time rather than they are really the guys who know how to do software architecture. So let's disentangle the three. The first one is your company can call you an architect, or you can call yourself an architect regardless of anything else. But that's just a job title. That's a role you might or might not play in the company. The second is the process of actually going through the analytical effort of engineering something, of architecting and designing something. And the final thing is the architecture, which is the engineering artifact that you're trying to build. So let's just relate this to bridge building, just to, by means of analogy. If you're building a bridge, you might have a title called principal engineer, right? Or you might not. Can you imagine a system where, an organization of the people in the team where you didn't have a principal engineer on the bridge? How would that work? You guys are familiar with agile software development? Agile software development, one of their process ideas is that you don't assign specific roles to people. You say, we have a team of people, we've got a bunch of work to do, we pick up work and we start working on it. So if we're building a bridge, we could divide up work the same way. We could build it in an agile way. And as long as we've all built bridges before, we actually stand a chance of that working out. Okay, so how might that work? Talk to me about how that would work.
A bunch of different people take small chunks and iterate on it.
So the bridge that just went up, the pedestrian bridge across 36, right? Presumably that's not a brand new bridge design, right? So we can sort of break it up into known chunks, right? Here's how you build a span that's this long, and here's how you make the foundations, and then somebody else is in charge of the logistics of closing 36 and moving the bridge over and deploying it or something, right? There, that's one way you could divide the work. There's no master architect, right? It's possible to do stuff that way. On your software development team, you guys are all broken up into teams right now, right? Not yet? When does that happen? Soon?
No, that's happening in 3 years.
Okay, so let's just imagine you're on one of these software development teams. You're going to end up, doing a lot of work together. One way you could do it is say you're the database guy and you're the middle tier guy and you're the UI guy, right? That's one way we can do it. Or we can all do everything, right? But it's just an organizational choice. There's nothing inherent about it. The process of architecting, let's go back to designing the bridge. The process of designing the bridge presumably should be done by somebody who knows how to build bridges, right? Is anyone in here a civil engineer? Okay, so that means nobody knows how to build a bridge, right? Should we build bridges? Okay, so one would suggest that no, I shouldn't be trusted to build a bridge, right? That there's specific training. What kind of things do they do? What do they? Do you have any friends who are in civil engineering? Okay, what do they teach them in civil engineering?
Take a lot of statics classes and a lot of classes on materials and that kind of stuff.
Okay, so they understand the materials they're working with, the properties they're working with. They can do mathematical analyses to figure out bending and breaking and all the conditions that the bridge is going to be subjected to, right? And they actually they run the numbers, right? Have you ever done anything similar? Has anyone ever done anything similar with software? Have you ever like thought through like, well, what happens if da 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 da, and like you work through it? It feels very informal, doesn't it? I mean, you do it. You definitely analyze the software, but it feels informal. And we're working towards, trying to make these things more and more formal. Here's an example. Microsoft, love them or hate them, is very, very concerned with security. Okay? A friend of mine was working there for an internship, and what they did was they built a formal model where a computer program could look at another computer program, figure out all the data files it could possibly read, and all the things it could talk to. And then they built this big graph. And it's essentially what they were trying to figure out is there a way that insecure data could come in, make its way through these different programs and end up in the wrong place? Okay? Sounds much more like what the guys are doing in civil engineering, right? Have you guys ever used any static analysis programs for computer programs? Yeah? What have you used? FindBugs is an excellent one. Yep, probably the biggest open source thing. Yep.
Splint.
Excuse me?
Splint.
I don't know Splint. I feel embarrassed. What does it do?
It's a static analyzer for C in addition to checking syntax also goes for bad practices.
Okay, so Splint must be derived from lint.
It is.
Yes, there we go. Okay, I do know lint. Okay, good. Yeah, so lint is trying to look at a static C program and imagine what happens at runtime. Does it leak memory? Does it have a free without a delete? Allocate without a delete, and so forth. Okay, so we do things like that in computer science, but mostly we're in it writing brand new programs all the time, and so we don't get around to the formal analysis stuff. And then finally, you've got an engineering artifact called the architecture. So at the end of the day, there is a bridge. At the end of our day, there is a computer program, right? It either does what it's supposed to do, does what your client wants it to do, or it doesn't. Okay? So here's the best way I would suggest you guys think about architecture. If you see cars on the road, you can identify which kind of car it is by looking at it, right? So you can say that's a Prius, that's a hybrid car. And this other one over there, that's a regular internal combustion car. Okay? So in other words, you can recognize the architecture even if you don't know what the roles were on the team, right? You don't know if there was a chief architect for the Prius, but you can still recognize the Prius. And you don't know whether they used an agile process or whether they used a waterfall process. You guys are familiar with those two terms, right? Okay, good. So, you don't know how they built the car, you don't know how they designed the car, but you can still see the artifact and see whether it's a hybrid car or not a hybrid car. And so the same way, we should be able to look at computer systems and say, that's a 3-tier system, and that's a peer-to-peer system, and that's a communicating processes system, and that's a shared repository system. So that's one way of thinking about this. Thinking back to Rackspace, with those 3 systems, even if you have no idea who built them or what process they followed, you can still identify the architecture. Okay, second big topic is views. I'm not going to belabor this one. You guys are all familiar with the idea that you can use a CAD program and you could draw a 3-dimensional version of a house, and then you can extract out a view of it that's only, for example, like this, the top-down floor plan view. Okay? And if I had a couple different views of my house, they could be consistent with each other or inconsistent with each other, right? I could have a first floor plan and a second floor plan, and when I actually try to put them together, I find out that the staircase is on one side of the building and then on the other side of the building, and that wouldn't work out, right? So what we do in software architecture when we're trying to design a system, to limit what we have to think about at any given moment, we might draw a picture. And the picture might be, for example, the communication path between the client and the server, right? Here's the sequence of messages that can go back and forth. What sort of things might you want to analyze that for? Like, I look at this sequence of events, what bad things might happen if I get that wrong?
You get stuck in loops or something.
I could get stuck in loops, I get some sort of deadlock, I could have 2 guys waiting for the other to respond and they never do. I could have messages that actually cross each other because they didn't get delivered on time and then I get the wrong answer. These are kind of things I want to think about. But then when I come back and I have to build the entire system, I still have to integrate that little view into the actual system, okay? And that's the crux of what we try to do, is that we as software engineers, is that we need to figure out a way to zoom in on the particular thing we're trying to solve, whether it's security or it's performance or is it I'm not going to get deadlocked between the client and the server. You want to zoom in on that with a view. Just take everything out of your way so that you're not distracted by anything else. Focus on that problem, solve that problem, and then figure out, did I integrate it back in here, or do I have, you know, the staircase is not lining up on the first and second floor? Okay? That's the basic idea of what you're trying to do with views. So the great thing about views is that because they keep you out of the distraction, you can end up having specialized views that help you with specific problems. Okay? I mentioned a minute ago the graph that Microsoft built so they could figure out if there was a security path problem. Okay? If you have houses and you have all these kind of different views, which one of these views would be the most helpful if you were trying to figure out, say, let's see, there's a leak on the second floor, how much of an impact is that going to be? Which kind of view of the house is going to be most helpful? Yeah, that would be good. Or maybe even just a two-dimensional picture with the pipes overlaid on it, something like that. I don't know, you can invent what you want to figure out the answer to these questions. What if you're trying to figure out, is the kitchen layout efficient for, you know, shuffling things around?
Map of the kitchen with furniture.
Yeah, and distances or something like that. Yeah. Okay. Yeah, I'm not trying to say anything rocket science here, but if you try to use the wrong view to analyze the wrong problem, that's not going to help you at all. Here's a true story. My brother does construction for a living, and architects for buildings have 3D CAD programs, but they don't always use 3D because it's a lot faster to draw two-dimensional views. So they were building this school, and you know, they dig everything out. They build the foundation. They do all the stuff. And they leave these holes in the foundation for where the water's supposed to come out or something like this. And then he goes and they pick up the other drawing, which is the elevation plan for where the ground is supposed to go. And he says, hey, buddy, you've got all these holes coming out underground. You know, they're supposed to come out above ground. But because the guys hadn't reconciled the top-down view of where the gradation levels were with the front view of the building where the holes come out for the drainage, they mixed up the two views and made them inconsistent with each other. Okay? So this really does happen to other people when they're moving too fast and making mistakes. Okay, quality attributes. Has anyone ever heard this term before? Have you guys ever heard the term non-functional requirements? Okay, so there was a little game being played outside in the lobby before we came in here. It's called George versus Vending Machine. And so there's one over here which says it's working but wouldn't take my money or my credit card. And then there's the other one over there that actually has a sign on it that says, a week ago we notified people this was broken. So if I walk up to a vending machine and it says non-functional, what do I expect? It's not going to take my money. Or it might take my money, but it's not going to give me any cool, refreshing beverages. So this is why people suggest we should not use the term non-functional for quality attribute requirements. So you've heard of non-functional requirements like performance and scalability, but let's call them quality attributes of the system rather than non-functional requirements. Okay? There's also another term, extra functional requirements, that people will also use. So a quality attribute is a dimension of quality used to evaluate a software system. I just named a bunch of them. Performance, scalability, throughput, latency, availability, usability, security. Anything else? There's thousands of these. Come on, guys.
Code coverage.
So that's a quality metric, yep.
Readability.
Readability.
For, like, coding.
Extensibility, right? You'd like to be able to have other people plug in certain kinds of extensions to it. One I'm dealing with on a project right now is deployability. These guys are moving from a standard engineers get together and statically collect a bunch of machines, provision software, and ta-da, it works. And they're trying to move into the cloud. And the cloud will be scaling up and down. And so what they'd like to be able to do is be able to make provisioning very easy and deprovisioning very easy and automate it so that they can do all these things. It's a quality of the system rather than a feature, right? The system doesn't do anything it didn't do yesterday, but now it will use more or less Amazon resources depending upon demand. Okay. So why do we study quality attributes? Because we believe that any architecture can achieve any feature, but if we choose the right architecture, we make the qualities that we want easy to get. So have you guys heard of this idea of a design space? So the idea is you've got all these different dimensions of your program. You'd like it to be fast. You'd like it to be cheap. You'd like it to be secure. You'd like it to be easy to extend, etc. So if you think about each one of those as being independent dimensions, what we are doing as software developers is choosing a point in that design space. And not every point is achievable. We would like to believe that if you choose any one of those, say performance, that if we gave you that task, you'd work at it diligently and you'd eventually end up with a system that was very, very high performance. And that's not the point. The point is, what did you have to give up in order to get that very high performance system, right? Do you guys know why people denormalize databases? There's two reasons. They don't know any better is number one. Okay, what's the other reason? Okay, question number one. What is denormalizing databases? What is a normalized database? Okay. See, this is where I'm saying it's much easier to teach people that have done this stuff before. In databases, when you put data into a database, let's say that I was putting in customer records, okay? And for my customer, I've got his first name and his last name, and his zip code, and his city, or sorry, his state code, and then his full state name, okay? So CO and Colorado, okay? And then let's imagine if I look at this database, though, if I look at this big list of stuff, I've got CO and Colorado repeated over and over and over again. A normalized database would say there's a separate table that lets you map between CO and Colorado. So you only have to say that once. You don't say it a bunch of different times, okay? Let's think about it a different way. Let's imagine for every customer record, you could have multiple phone numbers, right? And so if you were naive about this, you'd say Joe Smith, first phone number, Joe Smith, second phone number, Joe Smith, third phone number, right? Now you've got 3 rows in your database that all say Joe Smith. And then Joe calls up and says, actually, it's Joseph, right? And you update one of them and forget to update the other 2, okay? So that's a denormalized database. A normalized database would say, there's a guy, his name is Joe Smith, and then he has a phone number, which is in a different table, okay? So the point is, you can make things run faster if you denormalize it, but at the cost of repeated data. And when you update that data, you have to make sure you update it everywhere, okay? So choosing the design space is hard because you've maximized performance by denormalizing your database, but then you made maintainability hard because somebody needs to go through and edits become much harder, for example. Analysis. In general, you are going to be facing trade-offs constantly. More of this means less of that. If you are writing a video decoder, sometimes there will be special purpose hardware on your machine that will make that go fast, right? That would be very convenient. It might make it play very nicely. And that trades off against cross-platform, right? That if you take that code and run it on my computer that doesn't have that hardware, well, the code doesn't work, okay? So in general, there's a trade-off between portability of code and playback efficiency, okay? Another one is weight and speed. So for example, with cars, the heavier it is, the slower it accelerates, okay? And everything trades off against cost. Can you guys think of some standard trade-offs that you will almost always face with computer programs? Now, on any given project, there will be specific trade-offs that you'll discover. But are there general ones that you probably should know about?
Cost and time.
Cost and time. Everything trades off against cost. So let's choose one without cost.
Maintainability of time?
In what way is time?
Like, in order to make the code more maintainable, you'd have to take longer in writing it, make sure everything was working cleanly and commented and all that kind of stuff, so you know what you're changing later.
Okay, I'll buy that. Let's say that everything trades off against time to market and cost. Okay, I'll probably learn more things as we keep going along. You guys are good at this. Okay, does anyone have a bank account? Yes. Does anyone use online banking? Yes. Does anyone use two-factor authentication? Please nod your heads. Yes, yes, yes. Use two-factor authentication. Yes. Does your bank send you a text message to say you're about to log into your bank account? Does that take longer? Is it a pain in the butt? Why do you do that then? There's a trade-off between security and convenience, or usability is traditionally how we talk about it. Yeah, right? Yeah, you said convenience, right? Yeah. So yeah, this is exactly, you're always going to run into that problem, right? This could be something you're going to struggle with for the rest of your life. I mean, there's always going to be a security versus convenience. You'll be, a friend of mine's designing a system right now, and he's trying to figure out exactly how much security needs to be in place between the middle tier and the back tier, because there's lots of sensitive data back here, and if the wrong user gets to the data, that could be really bad. On the other hand, this thing is supposed to be authenticating that the user is the right person, so how bad should that be? Because he doesn't want this data to get out because he would get fired. On the other hand, he doesn't want to slow down the system and encrypt the connection and all kinds of stuff. So there's lots of trade-offs. So one way when we design systems, this is a technique that comes from the Software Engineering Institute, and Judy would know a ton more about this than me, is they have this concept of an architecture driver. Okay? An architecture driver is something like the trade-offs we just saw. It is a little story about what the system has to do and how quickly or how well, or some quantitative measure of how well it can do it. So here's an example of one of these things on the right-hand side. This is for example, if you were checking out books in a library. When a librarian scans a book copy for checkout, the system updates its records and is ready to scan the next one within a quarter of a second. Okay? What would happen if the system failed to achieve that? What sort of bad things could happen if it didn't do it in a quarter of a second? So what I'm thinking about is they pick up a book and go beep. They drag it across the scanner and it goes beep, and that's it. It's ready to go.
Pick up the next book.
And they're like, yeah, and it's too slow. And so now you're waiting to check out, and it's taking forever to get these things updated. Okay? Here's another one. When a librarian station cannot contact the main system, librarians can continue to check books in and out. Right? And so presumably it's keeping some local checkout records that get synchronized once the network comes back up. Okay? What bad thing would happen if we couldn't do that one?
If someone checks out a book online, it could still look like the book that someone just took is gone now, or is still there even though it's gone.
Well, here's what I'm thinking is that imagine you had a library and you had a bunch of different stations, and then back somewhere you've got the main server. And the bad thing that can happen is sometimes the network connection gets cut between the back office and the front office, essentially. And what this thing says is when that happens, you can still check out books. Okay? If you don't insist on that, you could build a system. In fact, it's a lot easier to build a system that requires the network to be working. Okay? But this allows us to keep running the library even when the server's down, right? It's a pretty convenient thing. If you have a paper-based system, can that failure ever occur? No, because there's no network connectivity that you need, right? You just keep writing it down on a piece of paper, okay? So this is a way of sort of making our computer networks act like no worse than the previous system we had with paper, okay? So here's the big idea with architecture drivers. You can write regular functionality scenarios saying like the user has to be able to bloody check out books, right? What these scenarios say is what are the qualities around that feature, okay? So the first one says must be able to check them out within a quarter of a second, and the second one says even if the server is down, you can still check out books, okay? So it's talking about the things besides the feature, the qualities that we expect the system to have besides the feature. And here's the real insight, is that what they found out at the SEI was that if you rate these things, and you see the HH and the MH, that means high, high, and medium high. If you have the business requirements guys, if they say this is a really important feature, they get to rate it high. And if you have the software guys saying this is a really hard thing for us to do, for example, the second one might be really hard to do. If you choose the ones that are rated really hard to do by software developers and really important by the business guys, you will end up with a reasonably small set of things. And if you get those things to work, all the rest of the qualities sort of come for free. I'm exaggerating a little bit, okay? But you think about it this way. If I could get these two scenarios working for library checkout, you might imagine all kinds of other things related to library checkout will also work the way you'd expect them to work, okay? okay? So in that way, these architecture drivers act as an umbrella. You only need to get a few of these architecture drivers right, the ones that are really important for the client and really hard for you guys to do. You write them down and you say, look, these are the ones we're going to pay attention to. And then when you say, I've got architecture choice 1 and architecture choice 2, you go back to these things and you say, well, which of these would be, which of my choices would make it easier to get these scenarios done? Does that make sense? Because otherwise you're going back to the drawing board and you're taking a look at your big requirements document and you're trying to say, how does this architecture work for this entire system? This says no. You can look at just a small subset of those things. Okay. Rational architecture decisions. Okay, could everybody do me a favor and stand up for a second? Excellent. Okay. I apologize for this. There's way too many yawns out there in the audience. Stretch. Okay. Oh, come on. Come on. Come on, put them up. There we go. Yes. Yes. Okay. Okay. When do you guys usually take a break?
Around 4:30.
Around 4:30. We'll get another hour then. No. Okay, so I tell you what, let's come back and we'll do rational architecture decisions when you get back. How long do you give them for a break? 3-4 minutes?
3-4. Say 10.
10? Okay, great. Thanks guys for being troopers for the first hour, and I'll see you back in 10 minutes. Break time's over, and we get to do more architecture, which I'm sure is exactly what you're hoping for. Yes. The good news is we're making good progress through the slides. The second bit of good news is we have a long class, and we have an exercise that goes after this. I think we'll be on time to get everything done. I was hoping that at the end we could have some sort of general Q&A. So maybe I'll go through a little bit more quickly here, and then we can get to the exercise, which is fun. The problem is we have to do this stuff before we can do the exercise, you know. And then we'll do Q&A and that stuff at the end. Okay. I'm going to talk about rational architecture decisions. The funny thing about rational architecture decisions is everyone assumes they're rational, right? No one says, yes, I am the irrational person that is going to make bad architecture decisions, okay? But here's the way you can make sure that you're doing the right thing. If you put it in this template, X is a priority, so we chose design Y, accepting downside Z. So for example, going back to the Skype versus plain old telephone service example from the very beginning, what's an example of what Skype was doing that fits into this template? What was a priority for Skype? Scalability, no central point of failure, ability to add new services quickly. Choose one of those. Okay, so we're going to choose scalability. Scalability is a priority, so we chose design what? What design did we choose?
Peer-to-peer.
Peer-to-peer. Accepting downside. Lower reliability, right? Okay. Let's try another one. Here's an example. Since avoiding vendor lock-in is a high priority, do you guys know what vendor lock-in is? Right, you standardized on Oracle's proprietary extensions, therefore it's hard to switch to another database. Since avoiding vendor lock-in is a high priority, we chose to use a standard industry framework with multiple vendor implementations, even though using vendor-specific extensions would give us greater performance. Okay? So the point is, at least you're telling people, we understood that we were making this trade-off when we walked into it. Okay? This can go awry, especially when someone thinks that they're, I talked about this earlier, doing something locally that seems like a good idea, but globally seems like a horrible idea. So imagine you guys are building your senior project stuff, and you've got 5 people on your team, and each one of you is in charge of a little bit of the functionality, and you choose 5 different databases. Seems like a bad idea overall, doesn't it? Like, it would be much easier to keep one database up reliably working rather than saying, well, I used Mongo and I used HBase, and then I used MySQL and I used a flat file, and can I think of another database? So yeah, there are certain things you probably want to get straight. Analyzing views, we talked about this a little bit earlier. The idea is if you choose the right view, doing the analysis is straightforward. Okay, let me ask you this question. Someone has asked you to analyze single points of failure in the system. Single points of failure in your system. what kind of diagram of the system might you draw such that you might be able to find those things? Let's say, for example, the client doesn't have a picture, but you can sit down with them and you guys can collaboratively figure out and sketch out a picture. What picture should you draw? First question, somebody tell me what a single point of failure is and why I don't want it.
It's a point in your system in which if that breaks, then your entire system goes down.
Excellent, I agree. You don't get to answer any more questions. Neither do you in the back. You've answered tons of questions too. Okay, good job, both of you, but we gotta talk to other people. So it's a single point of failure. It's a place in the system where if that one thing fails, everything goes down. Can somebody give me an example of a single point of failure? Yes?
If you have a wire internet connection, for instance.
Right, so if I have a company that runs off of a shopping cart system on the web, and I only have a connection to one internet service provider, and they go down, I stop making money, right? There's a single point of failure. And so what guys do is they put it in a location where they can get pipes from different vendors, right? Or they have multiple data centers, okay? So let's go back to the question. So what kind of diagram would you draw of the system that would help you find single points of failure? Well, let me ask you this. Are single points of failure usually related to your language choice? Not so much. Are they related to the dependencies between modules in your system?
Can be.
They can be. Are they related to the number of copies of software that you have running? Like if you have 3 copies of the web tier running versus 1 copy? Are they related to how data physically moves through the network, like in a physical way, like if a cable is there or a load balancer is there? Okay, so give me an example of a diagram that would be particularly unuseful. Would a class diagram be helpful? Probably not, because classes are usually inside some chunk of software, okay? And that one chunk of software, if I have 2 copies of it, I don't see how the class diagram is going to help me. Anything else? What if I was trying to figure out security? If I was trying to figure out if the bad guys can get to my data, what kind of diagram would I probably want to draw?
One that includes buffer sizes or something like that.
So that's a particular kind of security problem, exactly so, right? You can have a buffer overrun and they can exploit it. Now, what if that software were on one side of a firewall versus on the inside of my firewall? Would that make a difference?
You could.
Yeah. Well, it's
firewall configuration.
yeah. There's a defense in depth, right? You don't want them to get into anything, but if they got in behind your firewall, presumably they could do anything, right? The point being, generally, that you want to choose the view that helps you You ask the question, can bad guys get to my data? You want to draw a picture of your system, a view, that helps you answer that question, right? Because not every diagram of your system is going to help you. The corollary to this is that you will probably at some point, probably very soon, go work for a company that has a standard for documentation. And the documentation standard will say, step 1, draw a class diagram. Step 2, draw this diagram. Step 3, draw this diagram. And then you're done, okay? And if they've done this very well, there has been somebody who's been working at this company for a long time who knows what the problems that their software generally has. That is, he has asked those questions, okay? And therefore, he's put those kinds of diagrams, he's asked for those in the template to guide you to think about those things so that by the time you build the software, you're all set. If you go to a different kind of company, the same sort of template will be there, except there'll be 3 random kind of diagrams that don't help you with anything, okay? So that's a concern we've got here. Standard notations. Does anyone know UML, Unified Modeling Language? Yes, a couple people. Okay, definitely worthwhile. There's a couple really lightweight books. There's tutorials on the web also. The Martin Fowler UML distilled book is like the 20% of UML you use 80% of the time. It's good just so that it's got standard diagram notations for a bunch of different things. Its support for architecture is mediocre at best. It's usable, but not fantastic. But this quote from Whitehead is fantastic. He says basically, by freeing your mind of the unnecessary work, it focuses it on the problem at hand, and it increases the mental power of the race. there are what, 75 people in this class or so, 70, 75? I have no doubt that every one of you could come up with your own individual notation for doing architecture diagrams, and left to your own devices you would, right? UML may be imperfect, but if all 70, 75 of you guys use UML, you stand a fighting chance of understanding what the other person wrote down. No, I meant that the purple triangles are the load balancers and the blue squares are the, browsers. Like, who knew that stuff? And the dashed lines indicate that it's encrypted. Nobody's going to know that stuff. Use this notation and we all stand a fighting chance. Guide rails. Guide rails are one of the things that I think is relatively new with my work, so I'm kind of happy with this, and I tend to talk about it a lot. The idea is this: when you're given your project in a couple weeks, they're going to give you some constraints on the project that are very annoying to you. What's an example of a constraint that would be annoying to you?
Can't use a certain language.
Can't use a certain language. Anything else? Yeah.
Has to be on platforms you don't know.
Yeah, it has to run on the VAX that you don't want to program on, right? What else? What's another annoying constraint?
Certain database.
Must use a certain database. Must run in 64K of RAM. Yes. Must run on a 33 megahertz CPU, right? All this stuff really happens, right? And there's good reasons for it, right? It's running on a thermostat that already exists. You have to deal with it. My first job out of college, just so you know, was at Nortel, Northern Telecom, and they make half the telephone switches in the US. And they had hardware they started selling in 1976. The software we were programming on it in 1993 was compatible and could be run on the hardware from 1976. 1976, that's old hardware, okay, yes. And that hardware had to support 100,000 simultaneous phone calls. So those are annoying constraints. Those didn't help you in any way. So let me distinguish something else. What if I say on my system, have you guys heard of a 3-tier system before? Who's heard of a 3-tier system? Raise your hand. Okay, good. A 3-tier system is the #1 architecture you guys need to know about. A 3-tier system is what makes all what they call IT systems work. You have a user interface tier, you have a business logic tier, and you have persistence, okay? The idea with a 3-tier system is that you can swap out the user interface and your business logic is unchanged and your database is unchanged, okay? So for example, if you could have a thick client where you push a lot of stuff into the client and it runs a lot of JavaScript, right? You could have a thin client where actually they're just plain old HTML pages. But both of those two clients connect to the same set of business logic. For example, in a bank, you might have, I want to deposit money, I want to check my balance, I want to do that sort of stuff. So you write your business logic once, you persist it all in one place into the database. So that's what a 3-tier system is all about. One of the constraints in a 3-tier system is that the user interface doesn't talk directly to the database. Why would you think that would be a bad idea? Security. So for example, somebody could do a transaction that says only add money to my account, not transfer it from A to B. And if you just add money, well then we get rich. Right? Yep.
If you want to have multiple different clients in the same database, you have to rewrite all of your logic.
Let me see if I think we're saying the same thing. Imagine I have 2 different clients and they have a slightly different idea about how I'm supposed to store that data in the database, right? I can end up with 2 people trying to write data in the database in slightly inconsistent formats. Now the next guy goes to try to read it and it comes out bad for him. That's one thing you could do. But I think it sounds like you're shaking your head, you're thinking of something else.
Well, I was thinking about if you had, like you were writing something for a mobile phone, and that would be one of your clients, and then the other client could be like a web browser. If you just wrote all of your database logic in the web browser, and all of a sudden you want to add a mobile phone, it just screws everything up.
Right. So essentially, what you did was you have these core transactions that are common for all your different user interface types, and if you push that logic into the user interface, you got to rewrite it for each client.
Yeah.
Right. So that's what's called a 2-tier system. Right. You've got a database, and you've got the whole rest of the application. And so that's why they separate it out into 3, because then that way you could have multiple different applications. You share the transactions, which like add money to your account, take money from your account, checkout into your shopping cart, whatever the transactions are, okay? So imagine this. Imagine my system, my 3-tier system is running slowly because every time I got to hit the database, and the database is running on disk, and keeping it in memory is fast. So I do something very clever. I cache things in RAM on the middle tier, right? Where my business logic is, I cache it in RAM. Is there any problem with this so far? No. I need to check the cache, I need to check the database, I make sure they don't get inconsistent. But I'm the middle tier, I can do that. I'm smart, right? But now imagine that the user interface goes directly to the database. What could happen? Well, specifically, you're reading stale data, right? That I've got it in RAM and I haven't written it to the database yet. Okay, and I did that because I wanted to run fast. But that only works if I'm the only one, if I'm keeping those two things consistent. If somebody jumps around me and goes and looks at the database directly, they're going to get the wrong answer. Okay? So this is what this is all about. This is what this is a guide rail. So the guide rail that you would put on in this case would say, user interface never talks directly to the database. Why? Because it gives me, when I'm the implementer of the middle tier, the option of caching things and making performance go real fast, right? This is a constraint I put on myself so that I can make things go faster. But if someone breaks the constraint, I start getting wrong answers out of the system, and then that's no good. I don't care if it goes fast if it gets the wrong answer, right? All right, so the basic idea here is that if you do not constrain your system in any way, you cannot reason about what the system does and does not do, okay? If I said, here's 100K of code, what do you know about that code? Absolutely nothing, right? Could it erase my hard drive? Yes, it could do anything it wants. So in general, what we do is we constrain what the code can and cannot do. Have you guys ever heard of something called idempotency? Okay, this is a big deal for web architectures. Imagine that you've got a lot of work and you're going to divide it up across a lot of machines. And so there's a queue of work, and any machine can be allocated some little chunk of that work, okay? What happens if the machine dies in the middle of doing it? Well, you got to retry that work on a different machine, right? Let's say that it was something simple like resizing a photo from 1,000 pixels, everything gets down to 100 pixels for thumbnails, right? That was the work that needed to be done. So what you've got is you've got a farm of machines, you push out the photos to the machines, and they resize it and they hand it back to you, okay? Or they put it in a standard place, like put it into a database. Idempotency would say, it doesn't matter how many times you resize the photograph from 1,000 pixels to 100 pixels, you always get the same answer. If you do the work twice, you still get the same answer, right? Okay, what if I wrote this stupidly though, and what I did was I took the existing photograph and made it 1/10 the existing size, right? That's not idempotent, right? Because if I apply that thing twice, it went from 1,000 to 100 and went from 100 to 10, okay? And so you run into trouble. So what you want to do if you're building these big distributed web systems where machines and jobs are failing all the time, is what you make sure is that each one of those transactions is idempotent. So if you do it twice, that's okay. So you farmed it out, it seemed like the machine failed, but it actually finished up, but somehow it never reported back that it finished. If I ask somebody else to do it, they can repeat that same job, and I still end up with the right result. Okay, does that make sense? So that's an example of a constraint you put on the system so that you get the thing that you want. So it becomes easier for you to reason about, where you go, yeah, it doesn't matter if I schedule that job twice. I still get the right answer. I wasted a little bit of time, but no big deal. Okay? So think about this. There's a lot of examples where you design systems so that you constrain things in a certain way with the idea that you get a certain outcome. So for example, plugins must use cross-platform APIs to read files. Therefore, I get portability. This is great. I'm actually going to use an example you guys are going to know. Do you guys know about Xbox Media Center, XBMC? Yes. OK, I got one. OK. Do you guys remember back in the wild old days of Xbox Media Center where they had plugins written in Python and they never worked cross-platform? Do you know why that was? It was because of this. It's because they said, just write your plugins in Python. That's it. There were no constraints. So you know what people did? If you're writing on a Windows machine, you wrote your temp files to C:/temp, right? Which means it's not going to work on any other platform. insert any other sort of platform dependency, and it only takes one, and then the plugin doesn't work on the other platforms. So what do? Well, Xbox Media Center now has a cross-platform API that says, do these things if you want to save a file, and I'll handle it for you. Don't worry about it. Okay? In which case, now it's a lot easier to write a cross-platform plugin for Xbox Media Center. So what they did was they constrained the programmer. They didn't say, write any Python program you want. I believe it's Python, isn't it? Pretty sure it's Python. Anyway, now they say, write any Python program you want, except if you need to use the disk, then use this API, and I'll handle that for you. Okay? Here's another one. Enterprise Java Beans cannot start their own threads. Who knows what an Enterprise Java Bean is? Okay, what's an Enterprise Java Bean?
Some persistence application adapts to the object.
So Enterprise Java Bean is a Java technology for doing that middle tier programming. And what the container does is it creates new beans. As if lots of requests come in, it creates more copies of your program to handle all the requests that are happening. Okay? So the reason that they're not allowed to start their own threads is the container causes more copies of your program. So it says, no, you're a single-threaded program. I'll handle the concurrency for you, right? So out of that, you get manageability, where you don't have to worry about how many copies your program are running. Enterprise Java Beans also can't write local files because it'll possibly run your program on multiple computers. And if you're writing things to a local disk, and then it pops up more instances on a different computer, it won't be able to read the same files. So it says, don't write files on the local disk. Okay, architectural styles. We've been chatting about these as we've gone through. Let me tell you about the funniest one, which is the big ball of mud style. The big ball of mud style is what you get if you don't try to do anything else. Okay, that is, you get a little bit of this, you get a little bit of that. There's really no coherent anything. You can't separate any two parts of the program and say this is this and this is that. They're all just sort of welded together. Okay. The probably second most common is a client-server program that merely says, I've got somebody over here that requests things and somebody over here that responds to things. Can you imagine what sort of constraint I've just put on that program?
Requires a connection.
Yeah. Tell me about that connection between the two.
It's not always going to be there.
Can the server request things of the client?
Yes.
No. Nope, that's the constraint. That's the constraint. Because it says, look, this is the guy that responds, this is the guy that asks questions, right? So if you've got your user interface running in JavaScript, there's no Google servers that are calling your JavaScript, right? It's JavaScript that's calling into the Google servers, right? Pipe and filter. Pipe and filter is this idea, has anyone ever used Yahoo Pipes? Probably not. It wasn't very popular. But the idea was, imagine you had these little chunks of programs that could do a bit of processing, and then you could take their output and pipe it into the next thing. Okay? So in your house, the water comes in from the street. Let's imagine that it runs through a filter that cleans out dirt. Maybe it does, maybe it doesn't, right? Then it goes into a branch, and some of the water goes to your cold water tap, and the other of the water goes to your hot water heater, and then it goes to your hot water tap, right? So the idea is you've got a flow of water through your house through these different components that do work for you. So that's what the pipe and filter system is like. Let's imagine you have data that comes in from a satellite, right? The first step is get all the data, right? The next step is do error correction on the data that came in, because probably some bits got flipped along the way. So fix all that stuff. The next step in the pipe and filter is to separate it out into chunks, perhaps by picture or by day or by some time interval. The next step is to actually decode that and figure out what just happened, right? And then the final step is to recombine everything and put it into some log that says, this is what happened on this day. So that's an example of a pipe and filter kind of network. MapReduce. Does anyone know about MapReduce? Anyone who hasn't already answered a question? MapReduce is what makes the internet go round. So there was a reasonably well-read book by Bill Gates, and I can't remember the date on it. I think it was called The Road Ahead. And in this book, he was spelling out how he thought computing was going to evolve. And at this point, no one seriously thought that you could index something the size of the internet, and that is as chaotic and uncontrolled as the internet. Okay? In hindsight, the world is completely different. strangely enough, I can type in queries and get the answer faster from Google today than I can get my own mail server that's 15 feet away from me in the closet to respond. I mean, have you guys noticed how spooky fast Google is? I mean, it's like 50 milliseconds at worst, and a lot of times it's faster than 50 milliseconds. That's very, very fast. So it was perfectly understandable that a guy as smart as Bill Gates didn't see indexing of the internet coming. And the reason that we were able to index the internet is we broke it up into very, very small digestible chunks. Here's how they do it. You've got a lot of, let's say you've got a big database, or think of a lot of files on disk which represent web pages, okay? So you've got a spider going around crawling web pages, sitting them on disk, and then you've got somebody else that allocates work that says, I want you to go look at all the words that are in that web page. So some computer grabs that work and they create an index for that particular page that says, for example, the word the appeared this many times and the word computer appeared this many times and so forth. Now what you've got is you've got a partial index of that web page. And imagine doing that in parallel for a whole bunch of computers that you've got in a big farm, okay? So now you've got a bunch of web pages sitting on disk, a bunch of computers that are crunching through each web page and creating a little partial index, and then you've got another batch of processing that combines all of those partial indexes into a big index. And if you can do that with enough computers and crawl the web fast enough and recombine it fast enough, which Google showed how to do, you can create an index of the internet really, really fast. Okay? Really, really fast meaning like, I think they were doing it a couple times a day. Okay? They would have a brand new index of the web. It's pretty impressive, eh? And the only reason they could do it is because of MapReduce. So what is MapReduce? MapReduce is, I've got a bunch of work, I chop it up into little segments, I do the first part, which is the transformation from the input to a partial output. That is, in this case, a web page to a partial index. And then the reducing is taking all of those partial indexes and turning it into one master index. Okay? So imagine you were sorting numbers, right? I've got, or sorting, you have a phone book you want to generate. And you've got all these little files with people's names and phone numbers on them, and you want to compile a phone book. Well, what you do is you chop it up into different pages. You do the first little sorting. So now you've got a bunch of partially sorted phone book pages. And then you do the reducing step, which finishes up and sorts all those guys together. Does that make sense? So it's breaking it up into little chunks and then combining it together. Mapping is breaking up in little chunks and transforming. And then reducing is combining it back into one data set again. So that's how the internet works. Anything else you would like to know? Just kidding. All right, N-tier we talked about. N-tier meaning 3-tier. We just talked about that one. And layered is actually a different kind of pattern. Layered doesn't refer to the runtime part of the system. It refers to how your modules are organized. For example, if you say this module can call this module underneath it, and this thing can call this underneath it, but the ones on the bottom don't call the ones at the top. Okay? So the neat thing about knowing these standard styles is, first of all, not only can you sort of go through them in your head when you have a new problem to solve, you can say, well, would pipe and filter be appropriate? Maybe not, maybe so. You can sort of run through these. You can also know in advance which ones are good for what, because some of the trade-offs are cooked into the pattern itself. So you can also use this for communication. So when you're telling your friend, I just built a pipe and filter system, he goes, oh yes, I understand you built a pipe and filter system. Speaking of which, how many of you guys have read the design patterns book or know about design patterns? Okay, 20%. Okay, that's probably something you really got to know. Yeah, that's not optional. So if somebody says this is an adapter pattern or this is a factory pattern. Also, guys like me who will be interviewing you will ask that in the interview, and you should know what the design patterns are. It's just one of those things. Okay, conceptual model. This is the most abstract, fuzzy thing we're going to talk about. So if you get this one, more power to you. Hope it works out. A conceptual model is a set of concepts that can be imposed on raw events to give meaning and structure. So CU just had a great football game last weekend, didn't they? Pretty impressive, yeah? So the way I'd like to think about this is, imagine that I'm sitting watching that football game along with the coach of the game, okay? Are we watching the same game? That's supposed to be the easy question. Yes, we're watching the same game, right? So we see the same raw phenomenon happening, which mostly is the other team scoring, right? Okay, so when I try to figure out what's going on in a football game, honestly, I have to tell you, I can't always tell whether their offense is particularly good or our defense is particularly bad, okay? Now, do many of you guys find yourself in the same situation at times, right? Now, the coach watching the same game, he presumably should know, yeah, the guy should have been 5 feet to his left, and this guy should have been quicker, and he can see what went wrong such that things went the way they did, okay? Now, why is it that he can see that? Is that because his eyes are better than mine? No, that's not me. Not because his eyes are better than mine, right? Okay? So this is, no, just chew on this one for a minute. This is kind of interesting, isn't it? He can see things that I cannot see. I have a friend who's played basketball forever. I mean, I can barely play basketball. And so he can see, I swear, 10 seconds in advance that somebody's about to get picked off, right? Do you guys know what a pick is? When somebody like runs past another person, they lose the defender. Anyway, I can't see that coming because I'm a new guy to basketball. But he's like, oh yeah, the guy's gonna get picked. Yeah, it's pretty cool. You can see things that your friends can't see. Not because your eyes are better or worse. And I'm going to say it's because you've got this conceptual model. Now, you guys have all taken physics. And as a result of taking physics, you can't help but see the world in terms of physics, right? That a friend of mine was trying to tell me, I swear this is true, on her property that the well was down there and she was going to move the water up to the house and she was going to use it doing a siphon. And I'm like, no, I don't think you are. And she said, yeah. And I go, no, I don't think you are. Because otherwise, this would be energy moving uphill, and I just can't imagine this is going to work. Yeah. So it was just my understanding of physics that helped me believe that what she was going to do wasn't going to work. So what it does is it allows your brain to make sense of all this raw phenomenon that's going on. And it makes sense of what otherwise would be chaos and too much stuff to comprehend. Like me watching the football game, chaos. The football coach, he understands positions and plays and arrangements, and he understands what things should be happening compared to what they are happening, and so he just can pick up all that stuff very quickly. So here are examples from other domains. We already talked about physics and we talked about sports where these guys are running plays, and that sort of diagram of what's supposed to happen, that's what's in the coach's head. And so he's comparing what really does happen compared to what's supposed to be happening, and he only has to pay attention to the delta. Right? He only has to pay attention to the one guy who was in the wrong place. Whereas I'm trying to make sense of everything for the first time. When you take economics, they tell you about supply and demand. You can't touch supply and demand. There's no physical manifestation of it, but it's a concept that helps them understand how prices get set. When you do accounting, they talk about debits and credits, and that helps you organize the world such that accounting works out. And if you care, there's a video on my website where I talk about the energy cycle in dandelions that people thought was funny, but you can think about that too, about how many times you need to pick a dandelion before it doesn't come back, right? Depends on how much potential energy is in the root, for example. But that's my mental model. Maybe I'm wrong, but that's my conceptual model for going forward. So you guys are in the unenviable situation of being like me watching football going on, right? I am in the enviable situation where I've been formally trying to understand how software architecture works, and so I have this rich conceptual model, and Judy has this rich conceptual model over her head. When she sees a system and it looks sort of like a three-tier system, except that it's broken in this certain way, it pops out to her and says, did you guys realize you did this, and if you did this, the implications of this would be the following? Judy's gonna be like right on top of that because she's seen it before. So here's what I think my conceptual model of software architecture looks like. And we all know that it's very hard to reflect and say what's in my head, but I think this is what's in my head. That there's model relationships like views and view types, there's designation refinement, there's a standard structure of our models that we're going to talk about in a couple slides. We already talked about quality attributes, there's design decisions, there's trade-offs that you're making, there's responsibilities that you allocate. When we talked about the three-tier system, we said the user interface does this, it's responsible for this. The business logic is responsible for transactions like debits and credits. And then the persistence tier is responsible for making sure it gets saved on disk. We talked about constraints. We didn't really talk about view types. And basically this is the way I think about software architecture, okay? And I think this is what allows people who are expert to be expert, rather than just getting old. Here's more good news, bad news. The good news is, as you get older and you build software, you get better and better at this, whether you try or not, okay? The bad news is, you're gonna get old, okay? And you don't wanna have to wait until you have gray hair like me before you understand this stuff. It'd be great if you're 25 years old, you understand all this stuff, you make good decisions, and your startup makes you a billionaire. That's what you'd like, yes? Right. Rather than you don't understand this stuff, you guess wrong on how to build the system, and your startup does not make you $1 billion, right? That would be the bad case. So, next is engineering with models. And I apologize that this feels like this grand tour of software architecture, but I'm trying to show you the good bits that are useful rather than like walking through an example. So why do we use models? In general, whoa. Oh, is that just the computer deciding it's going to turn off? Okay, it's in warm-up mode. So I'll just talk for a bit. In other engineering fields, we talked about this. You probably have friends who are civil engineers, mechanical engineers, nuclear engineers, you name it. They all use models, right? Why do they use models? Why don't they just work on the problem directly? We work on the problem directly. We fire up a command line. We say, start MySQL. We create a schema. We push it in there. We, make some transactions. I mean, why don't they just do that stuff?
Having that abstract understanding of what you want to do really helps with guiding you what path you're going to take to get there.
I'm going to agree with that, but I want to know why the civil engineers why don't they just start building stuff? Yes?
It's more expensive.
Yes, we have this lovely situation that we can get stuff done quickly and without any cost. The electrons don't cost very much money compared to what cement does, right? I completely agree. Any other reason that they use models? Yeah.
Because you can have completely different, like, the earth matters, like what type of soil you have. There's so many different things you have to take into account before you just start building.
Right, and what's more, that they understand those, right? So if you take one of their handbooks, they've got these properties of the materials. They talk about standard designs and how they can be analyzed. They have analytical techniques. A lot of things that we're comparatively impoverished on. On the other hand, they've been building buildings for a couple thousand years, and math was developed to explain how physics in buildings work. Okay, we're farther behind, but some of the stuff that we do is pretty cool too. Anyway, the point is, a lot of times we immediately reach for tangible, let me start hacking it up, and they reach for a model. And the argument I'm going to make here is that many times we should start thinking with models too. Not all the time. Sometimes you're like, look, this is just so easy, I can build this. But other times you really want to think about using the model to make sure you got your math correct before you move on too far. So here's a basic diagram that shows what you're doing. I know it's sort of weird to spell it out like this, but your goal is to start with a real-world problem and create a real-world solution. And sometimes we can just start typing, we build it. In the same way, if somebody says, here's a piece of wood and a saw, can you make this piece of wood look like that? You're like, yes, and you just sort of do it, okay? If it's simple enough, you just do it. But if you can't, what you do is you create a model version of the real world, okay? And what that does is it loses details. You keep only the details that you think are important to solve the problem. If you had this problem down here about the two trains traveling towards each other, one train is red and one train is blue down here, but when I talk about the model, I ignore which colors they are, right? Because for some reason I think the color is not important, okay? And when we build our software models, we need to do the same thing. Now that we've got a simple version of the problem, perhaps it's just simple enough that I can solve it, okay? But I'm solving it at this abstract level. And so I say, what I need is a protocol between the client and the server that does the following thing, and I build that protocol. And then what I need to do is actually write the code that does that thing, okay? Now, is it easy to write code that does what you want it to do? No, I would say in general it's not. I mean, when you guys did your data structures course, that was all about, yeah, I understand how a linked list works, but then actually writing a linked list that doesn't break is actually kind of hard. Or at least it is when you start, right? And then writing an implementation of quicksort is actually kind of hard, right? To get it actually right. So this is the basic idea of what we're going to try and do with software architecture. The real world problem we've got, build Google or something like this, right, is gigantic. It's too big. So what we do is we make a smaller version of it that it elides some of the details. And we say, hey, if we do the following things, maybe we can actually solve the problem. Great, now you've got a paper solution, and your job is to actually make the thing really work. Okay? Does this make sense, sort of what we're doing and what your friends are doing in civil engineering? Okay. So this last section, I think, is really pretty important on the canonical model structure. And what I'd like you guys to do, because you're not ready for this section, no offense, but just put a bookmark on this and maybe come back to it later and say, I know that there's a standard pattern to these things, and you can look it up. So it's the following. Let's imagine you are building, let's go back to the bank. In the bank has accounts, right? And it has transactions like transfer money from one bank account to another. Let's talk about that idea of transferring money from one bank account to another at different levels. What I call the domain model up there, let's say that I'm the customer of the bank. I mean, me. You can touch me, right? I'm the customer of the bank. Down here in the code, you can't touch me, right? Right? I'm not in the code, right? But there is a record on a database somewhere that says George Fairbanks, okay? The two things correspond to each other, right? Now, in some ways, they must correspond very, very carefully, right? If I take $100 and I put it into the bank, in the real world, up at the top, in the domain model, down in the very bottom, the record that the computer keeps must be consistent with what really happened in the real world. Otherwise, I get very angry or they get very happy, right? Right? Does this make sense so far? Okay. So in the middle, what you're doing is you're designing software that's neither me as a physical person, nor is it the code once it's written. Okay, so the bottom is the code and the databases and the hardware and everything else, okay? In the middle is how you're thinking about solving the problem. And what you need to be able to do, and it's hard, is keep consistency between these three things, right? I can't help in the real world but get a day older every 24 hours, right? I could make a bug in my design or in my code such that I don't increment my age in the database and I stop aging, right? I could make that bug, and that would be a bug in the program, okay? There are certain things that can happen in the domain model that you'd like not to happen in the code model. So for example, I can physically go in and rob banks in the real world, right? But I'm trying to do everything physically possible to make my code such that bad guys can't come in and rob it in a different, intangible way. Or think about this. When you try to explain to your parents that a hacker has gotten a virus implanted in their computer, stolen their bank password, and has stolen all of their money, they're like, did they go to the bank? No, the bad guys never went to the bank. I'm sorry, I'm trying to avoid saying any particular kind of hackers. I usually say where the hackers are from, but that's probably not necessary. They're bad guy hackers, and they've stolen all your parents' money. And you're trying to explain to them, no, Mom, the bank is fine. The physical bank never got touched. It's just the record of ones and zeros, and then you're trying to explain to them, like, at these different levels of abstraction, what just happened, okay? So when you are designing software, you're working at this level. When you're drawing pictures of the code, you're working at this level. No code exists yet, right? And yet you're not physically, you're not dealing with, like, that bank account or the money or any of those real things. So what you need to be able to keep clear in your mind is these different kinds of models and which ones you're drawing right now. Which kinds of things can happen to people in real life, which kinds of things can happen in designs, and which kind of things can happen in code. Okay? Another corollary to this is that when you, let's say you start a new project, who uses Subversion? Okay, who uses Git? Okay, great. Either way, you start a new project, what does the directory structure look like inside that project? Brand new project. Could be anything, right? No. No, this is what I'm trying to say, is that you've got some facts about how the real world works, you've got some facts about the designs you're considering, and you've got some facts about the actual source code that you've written, okay? So when you guys start up your project in a couple weeks, think about that. There's going to be facts that the people are going to tell you about the domain that you're going to be working in. We work with lasers, and we collect data from the laser experiments, and we bounce this laser off the moon, and we collect measurements, right? That's the real world. That's really what's happening. We'd like you guys to build us a system that works across time zones to gather that data and to batch up some analysis of the data and store it in a database so that anybody can access it, okay? That's your design, right? You're going to start designing the system that would actually do that. And then you're going to write some code, and that's the third part, right? So right off the bat, you just learned something here today. In 2 weeks, when you start out your new Git or your Subversion project, you're going to have 3 directories, right? Stuff that they tell me about the factual world. There's stuff that I'm designing and may or may not actually come to pass. And then there's code that I'm going to write. Okay? So useful to think about this. It's like the coach talking to the rookie again. Like, you know, here's a pattern you're going to see over and over for the rest of your life. Okay. Models and code. You'd like to believe that the software architecture of a computer program, just like when a Prius drives by, I can see the Prius and I can recognize the Prius. You'd like to believe, wow, here comes some program, here comes Skype, Zoom, and I can say, oh, that's a peer-to-peer system. But actually, it can be really hard by looking at source code to figure out what that thing does. Are you guys familiar with the obfuscated C coding contest? The ones of you who are have a big smile on your face. The ones of you who do not know about this have a new homework assignment. Look up for the past winners of the obfuscated C coding contest, and you will not believe the kind of code people can write that does exactly what it's supposed to do, say calculate pi, but it looks like a camel. Like they formatted the code with semicolons and underlines, and it looks like a camel, and then when you run it, it calculates pi as long as you want. And you're like, how can this possibly do that? And that's the whole thing, is trying to, that's the obfuscated C coding contest. Now, I'd like to suggest that not all C code is as hard to understand as what they write, okay? However, left to our own devices, it seems perfectly obvious what this code does at 11 p.m. when I wrote it. And 2 weeks later, when I'm trying to figure out what the heck I was doing and why did I increment I right there, why did I do this math plus 3 divided by 2, I have no idea why I did that stuff. So that's even at the like single lines of code level, let alone I've got a whole pile of code and I'm trying to figure out what the architecture of this thing is. What about things like when we talked about the user interface shouldn't talk to the database? How do I write that in the code? Any ideas? It's really hard to write that in Java, isn't it? The user interface should not talk to the database. Hard to say what it shouldn't do. You could write it as a comment, but nobody reads the comments anyway. Where would you put the comment exactly? See? So what I want you guys to get to understand here is that architecture and code are very different. It's one thing for us to sit here and go out on the whiteboard and draw pictures of architectures and boxes and lines and everything what's going on. When you get down in the code, it's really hard to figure out what's going on. So one thing you can do is you can drop hints. You can drop little clues for people that come after you and try to figure out what your code does. I would suggest that you already do this. Do you guys name your variables x1, x2, x3, x4? You do not. Why do you not name your variables x1, x2? Why should they be called anything else? It takes longer to type long variable names.
I don't want to claw my eyes out later trying to figure out what's going on.
Well, why is it hard to figure out? What is making a long variable name? Why is it easier to understand?
Description.
But tell me more.
And that's the kind of insight as to what that variable actually does, rather than just some arbitrary string that represents it.
Okay, so let's say I have x, and x is an integer. What can you tell me about what this program does? You can hardly tell me anything. What can you tell me?
Well, if, depending on the names you use, if I use names that make sense, then x might be the, like the point on a graph, x, y. variable.
Good point, right, yes, I'm with you there.
But like, that's assuming every other variable made sense, and yeah.
So let's take one step back. So I can make every single variable in my program a string, right? And then just convert it into the type that I need at the time. But I don't do that. One reason is efficiency, But another reason is because somebody's going to come along and read this and say, oh, that's a floating point number as opposed to an integer. That probably means something, right? It probably means that, sorry, I hate backing up in slide decks, but I'm going to do it. It probably means something about the domain. Number of children that I have should not be represented as a floating point number, right? In America, yes, 2.2 kids per family, that's fine, but not for any individual family should not have 2.2 children, okay? So what you do when you write the program is you choose a data type that communicates something that you know about the domain, something that must be true. You're communicating that to the person who's reading the program. And you know who's reading the program? It's you 2 weeks later, right? When it's not 11 p.m. and you're trying to figure out what you just wrote, okay? So you write this stuff into your program so that you stand a fighting chance of recovering that domain knowledge about how stuff works, so that you stand a chance of recovering that design knowledge about why you decided to lay it out in a certain way. And so you go beyond what the compiler needs. The compiler just needs X, right? But what you need is total expenses as the variable name, or number of children, okay? These are good variable names. But that's just the beginning. What if in your project you were trying to communicate to somebody that this is a client server? How could you possibly do that? It's a client server architecture, and somebody's going to read your source code and try to infer that. What sort of clues can you drop to indicate that that's the case? Yeah?
Two different projects, one called server, one called client.
I agree with that. Or you could have two different directories, right, under the project and say this is the server folder and this is the client folder, right? As it turns out, that's a great one. It tends to break down because you end up having shared libraries and sort of goofy stuff that ends up messing it up. But it's a great first step, right? And it works a lot of times. Anything else? Yeah?
So in different variable names, say client is sending to server, say client number of children, send to server number of children.
Yep. What about your class names or your module names, right? You're going to have a file that's sitting on disk. It's going to be called client.py, right? This is a great way of indicating, aha, this is probably a client-server pattern, right? So what you will notice is that there's some things that are really easy to express there, and some things that are really hard. The negative things are really hard. Don't do the following thing. Whenever you do X, also do Y. These things are nearly impossible to say in the code as we have it right now. Okay? But on the other hand, really, when you write your programs, think about somebody else is going to have to read this. What sort of clues can I drop so that I can recognize what I did later on? Okay? So that's what this idea of an architecturally evident coding style is, that we use things like total expenses instead of T. We express the architectural ideas, and the advantage is we avoid problems because people understand what we're doing and why. We improve developer efficiency because they spend less time reading code. Oh, since you guys haven't heard a lot of stuff, this is great because you don't know this stuff. I can say again for the first time. If you're a practicing programmer, what percentage of the time are you spending writing code, new code?
15%.
Yeah, it's some small number. You can, depending which study you believe, but I heard 5 and 15%, which are probably in the right ballpark. What do you spend most of your time doing? The biggest single thing that you spend your time doing? Debugging is a good guess. It's not the one that I've heard. Reading old code and trying to figure out what stuff is going on. The bigger the system, and you've got a bug you got to fix, maybe it's your own code, maybe it's somebody else's code, maybe you're just trying to extend it, you're trying to figure out which 5 lines of code you've got to write to make it do what you want it to do. Oh, here's another one that I need to get on you guys about. Does anyone know the difference between a library and a framework? Okay, you've heard these terms sort of used interchangeably. This is the user interface library. This is the user interface framework. Okay, think about it this way: a library is a master-servant relationship. And when you call the math library and say, "Calculate the square root of 5 for me," it calculates the square root of 5 and hands it back to you, right? It's the oldest kind of software we use. It goes back to like 1948. The subroutine was invented. So you'd say, "I'd like a square root, please." You hand it a number, and it gives you back the answer, right? You are the master, it is the servant, okay? When you guys do user interface programming, do you ever have to deal with callbacks? Do you guys know what a callback is? Or register for an event? Okay, event handlers, this kind of stuff. Notice the difference. Who's the master? Who's calling who? It's the framework that's the master, and it's calling your code. If you want, for example, let's say you've got something that runs inside the browser, and there's an event called paint, or a method that you override called paint. And what you do is you draw your stuff on the screen when it says the paint event has occurred, or I've just called you with the paint callback. The master-servant relationship has been inverted. You plug in. So the advantage you get with frameworks is, let's say you're running Microsoft Windows, and you, a program inside of Microsoft Windows, or GTK, or whatever it is. The point is, you only have to write a very small amount of code to get something to appear on the screen. That's great. And like you can resize that window, you can even print screen that window and print it, you can do all kinds of stuff that comes for free with the framework. The downside is you're not in charge anymore, right? It's not like you're down at the C command line being able to write any daemon process you want where you're going to run autonomously. Instead, you're running inside of a framework that sends you events and you respond to them, okay? So that's the primary difference between a library and a framework. So when we talk about improving developer efficiency, you spend a lot of time inferring what the other code does. It's really great if you could signal to other people what your code is doing. You lower the documentation burden because you've sort of built the documentation into your code. And new developers get up to speed faster. Last section. You guys excited? Okay. Before my book came out, my book's called Just Enough Software Architecture. The idea behind my book is that you probably don't want to do a ton of software architecture. It's focused at developers. You're probably not architects, but you do need to know some of it so that you can get some of it done. Big idea is the following. Architecture had been explained mostly, I think I'm going to try to say this as fairly as possible, and I don't mean any disrespect, as fairly as possible to say it had been done by people on extremely large projects. So for example, if you went to the SEI, usually you're the defense department or a defense contractor, and said, I need to build a battleship. I need to build a new strike fighter. I need to build a cruise missile. I need to build a system that will consolidate information from everyone on the battlefield and then display real-time status. Okay? I hope no one in here wants to build those kind of systems. Okay? What I mean by that is, this to me sounds like a nightmare. It sounds like I'm going to be, up, like pulling my hair out, just worried about how I'm going to make these things work. Very, very hard problems at the very edge of our ability as engineers to do these things safely. Okay, so imagine you're doing this stuff and you're trying to understand software architecture. You invariably then are looking at projects that have this very long design phase, and then it fans out to a bunch of software development teams that you're going to coordinate and march together. So this big project becomes very waterfall-like. Okay? And it sort of by nature has to be. Now let's compare that against you're building a website. Okay? Now if you're building a website, this is a pretty easy thing to do. There's a lot of code already out there. It's a highly precedented system. There's a lot of reusable assets like MySQL for a database, or a web framework for building this stuff, or a JavaScript framework for getting this stuff working on it. And the browser by itself, by the way, is already invented. We're in a completely different zone. Does this mean I don't need to pay any attention to software architecture? See, this is where I don't think you can ignore it completely, because I think you can run into trouble. At the same time, you shouldn't treat it like you're building a battleship. So you want to figure out how to dial that in. That's what this is about. There's this great historian of software, of engineering, Henry Petrosky at Duke University, and he's written a bunch of really cool books that if you're sort of an engineer dork, he writes about how pencils come to be. And it turns out a very complicated story, because there's paint, there's wood, there's graphite, there's a little piece of metal, there's the eraser, and how all those things come to be and come to be assembled. Really cool book called The Pencil. Okay? He writes about engineering in general. The concept of failure is central to the design process, and it's by thinking in terms of obviating failure that successful designs are achieved. Although often an implicit and tacit part of the methodology design, failure considerations and proactive failure analyses are essential for achieving success. And it's precisely when such considerations and analyses are incorrect or incomplete that design errors are introduced and actual failures occur. Now, if you're building a battleship, all you're thinking about is, how can it go wrong? How can I end up shooting the wrong guys or sinking the battleship? When you're building a website, you have things that can go wrong. Let's just say we're building a website today. Which things would you be worried about? A small website for our family.
Broken link.
Broken links. Yeah.
The
different appearances on different browsers.
Yep, so compatibility between browsers.
Backing up the database, backing up.
Failures, right? Hard drive crashes happen. Yep.
Long delays, like when trying to get the website to work.
Could you say more?
Or, just like
Development time?
no, for the user when they go on the website.
The latency of clicks.
Yep.
Yep. You want it to be quick and snappy and responsive. Okay. So let's think of ways now that those failures could occur. Obviously, hardware failures are really not under our control. The latencies are all up to us, right? How could we make a website that's really slow to use? Bad queries, right? We could have a database with bad indexes in it. We could write stupid queries in the first place. We could have the data in the wrong places, so it's hard to get to. Anything else? What were the other failures?
Broken links.
Broken links. How could we end up with broken links? How can we avoid them?
Test them before you push your changes.
Okay. But you see what we're doing here is we're not doing like battleship kind of analysis, but we're starting to look at like, okay, what are the bad things that could happen? What are the things I could do to prevent it? And like this might be a 5-minute exercise. But the point is you at least want to walk through these things. And if you don't think about how it can fail, you're probably going to be looking at the success case the whole time. Like click, click, click works for me. I'm using Chrome on Linux and the layout is perfect. And I never thought to look at grandma's Internet Explorer and see how it renders on that computer, right? But it's not like it's rocket science. You just have to think about the failures and figure out what am I going to do to try to avoid them. So what Piotrowski says in a nutshell is what you have to do is think about failures, analyze the options that you've got for design, and choose a solution that minimizes failure risk. But what you can choose to do is when the design is actually going to happen, which analyses you perform, how much depth or formality or precision you're going to do on those things. Okay? So you could choose to do nothing and you might get really bad results. You might be really unhappy that the latencies are bad, for example. So here's the actual inspiration I had for this. When I was a kid, we had the car parked in the driveway, and it was on a very small slant. And my brother used to like the noise it would make to release the parking brake on the car. It made punk, make a funny noise, and he loved that noise. So we'd get in the car, and he's like, pull this thing, and the car would roll in slow motion down the driveway, knock over the mailbox, and this happened like 3 or 4 times, okay? It probably only happened twice, but you know how these things get magnified. Anyway, in my brain, this was happening all the time, and so it felt like my dad was always replacing the mailbox. Now, my dad is a mechanical engineer, and yes, that is my dad, and what he would do is he would dig a hole, stick in the post, fill it with concrete, and just be on his way, right? He could do mechanical engineering analysis to figure out the stresses and the strains and figure out how much concrete and how big the hole should be and how heavy it should be and what the moment is on this thing if it's going to blow in the wind, but he never did any of that stuff. And so the idea is what you need to do is you need to tune this in based upon how much risk there is. And he's looking at this saying, this solution is just not going to fail, right? There's enough concrete. It's not going to get blown by the wind very hard. You know, if this thing were 20 feet tall, I'll worry about it. But it's this tall, it's just not a big deal. So how can we do software roughly the same way? And so here's the first insight, is we spend the right amount of effort depending on our risk. So when we think about this website, we're thinking about like half an hour's worth of noodling over this, maybe going, what are the things that could go wrong? What can I do about it? How bad would it be if any of those things happened? Okay? If you were a bank, you might be worrying about how will the server scale up? Will the bad guys steal my customer data? But you might also think, well, actually response time is not going to be too bad, and we actually have plenty of RAM in these systems, right? We're not like dealing with a phone that has limited RAM. So we want to then cast these worries as engineering risks. And we say, this is the way that my system could fail, and we focus our energy on the highest priority risks, okay? And here's the good news, is in general, I find that if you ask developers who are on a project, like, what are you worried that could happen that would make you embarrassed? They're like, let me tell you, right? They're like right with you. They're like, boom, here's the stuff I'm worried that will go wrong. So that's good news. They're pretty good at figuring out those. The second bit is you want to choose engineering techniques that'll get you out of that risk, that'll show you that your design does or does not work to get you around that risk. So here are some techniques that exist today. Protocol analysis. If you're worried about the client and the server getting stuck, there are ways to analyze protocols. There's component and connector modeling. We've sort of a little bit seen this. Judy, I'm sure, will talk about this. The idea is that I can draw stylized pictures of my system that make certain kinds of errors just pop out. There's queuing theory, there's schedulability analysis, there's threat modeling, and so forth. A lot of the techniques that we use most often are informal. Interestingly enough, in other domains, a lot of the techniques they use are formal, right? Tungsten has this particular modulus of stiffness, and I can work with that. The techniques are not interchangeable. If I say I'm really worried about security, and I'm going to say my technique to do that is to build a UML diagram of my classes, I haven't done anything. I've done busy work, right? I haven't done anything to address the failure risk, okay? If instead I say I'm really worried about security, what I'm going to do is analyze all the different vectors that somebody could get into the database and try to minimize them and secure the connection and whatever. That seems like a way that's a path forward. So you have to match the risks with the techniques. In other words, don't say on every project, I'm just going to do these following techniques. These are the appropriate design techniques to do with the project. Instead, you want to say, on this project, this is what I'm worried about. I'm going to choose these techniques. Let me think about it. Let me put it a different way. If you have one team, you guys are going to build your little web application. One part of the team is in charge of the user interface. One part of the team is in charge of the database with credit card numbers. Are you guys worried about the same things? No, I mean, clearly the guys with the credit card numbers are, like, all they're worried about is how can the credit card numbers stay in the database and don't go out, right? That's bad. But you need the credit card numbers so you can bill them every month for the service or something, right? The UI guys are not worried about security so much. They're worried about latencies. They're worried about refresh. They're worried about browser compatibility. They're worried about how hard it is to develop. They're worried about how easy it is to drop in new CSS and reskin the user interface, right? So the design techniques that you choose have to be appropriate to the failure risks that you're looking at, okay? And that can vary even within your same team. So here's the risk-driven model in a nutshell. And so you can use this to sort of guide how much design effort you put into things. First, identify and prioritize your risks. If you haven't thought about it, you can't really do anything actively about it. The second is you apply relevant architecture activities, and more often than not, you'll be inventing something ad hoc. But guess what? It's better to do something ad hoc than to do nothing at all. And then third, you reevaluate. And the way I express this is, if it drops off your radar as being really a risk, you're done, okay? If you say, I'm really worried about the credit card numbers leaking out of the database, I did the following thing, and I'm still worried about the credit cards getting out of the database. Guess what? You're not done, right? Keep going through until you figure out something that gives you confidence that that bad thing isn't going to happen. So the problem here is you need to balance wasting time on low impact techniques versus ignoring project threatening risks. There's a great story about the Wright brothers. The Wright brothers, when they were the first guys to fly, they weren't just the first guys to fly. They were the first guys to actually try to develop the equations that would describe what was going on with the airplane. So they were doing tests, and they were trying to infer what the equations were for how things work. They were taking measurements. They were doing experiments. They invented wind tunnels and all this sort of stuff. But they also wanted to be the first guys to fly an airplane, right? They could have spent longer, fully understood aircraft mechanics, and not been the first guys to fly an airplane. So you always have this desire to ship the product. You have this desire to fly the airplane, right? And you often will fly the airplane before your risks go to zero. In fact, let me say that a different way. You will always fly the airplane before your risks go to zero, okay? You will always do that. They may be very low, but they'll never go to zero, okay? So let's think about the rack space example we talked about earlier. As far as lean or agile architecture, the agile processes, they could have followed these, and they have relatively few design techniques. In architecture, we have a lot of different design techniques. You can pick up any number of these books, and they'll show you how to draw lots and lots of different kinds of models and do analyses. But what you want to do is you want to use the risk-driven model to combine these things and figure out what is the right amount of formalism to use here, what's the right amount of analysis to do here. So with Rackspace, did they proceed rationally? Should they have done big design up front and said, in 2 years, we will need to be at the architecture version 3? Okay? What are the risks of doing that? What bad could happen if they jump immediately to version 3? Spend a lot of money, spend a lot of what goes along with money. Time, right? Because they're trying to run a business, right? So in the meantime, they've got no searching for the logs while they're setting up a Hadoop system, and it's much more complicated, a lot more moving parts, right? And they just didn't need it, right? So maybe they were exactly right to do the first one. Did they know that, for example, like a lot of you guys in here suggested, or at least one of you suggested, let's centralize the log files in a relational database. Is it obvious that the relational database is going to fall down with this volume of logs? Not to me. I was actually kind of surprised to learn that it didn't work out for them, okay? So yeah, it's just not clear. So if you were Rackspace and you were at the very beginning here, how would you characterize your risks? What sort of risks would you say we are facing as a company? What risks would be keeping you up at night? What would you be worried about? And I want you to think in the big picture. Your job is to run a hosting provider for mail servers, and this is just one of the many things that could go that's going on in your life. Yeah?
More importantly, would be servers dying.
I'm much more worried about hardware failures. I'm worried about monitoring. I'm not so much worried about handling CSR requests, customer service rep calling in and trying to figure out what's going wrong. I mean, I know I need to handle it, but it's just not honestly the thing that keeps me up at night. Because if I'm a hosting provider and my mail servers don't work, people are going to fire us. Okay? So my first risk is trying to make sure the service works, and the second one is trying to figure out how I can optimize, minimize the size of the log files, or how much infrastructure I need to build. So I would say that actually this is probably a pretty normal progression. You just make something that seems to work. It's not completely stupid, and it worked for a long time until they said, oh well, actually too much load on the servers. Push it into MySQL. Worked for a couple years. Push it into something else. Okay. So good news. This is the last slide. What we've done is a big survey here, and what I've tried to do with this big fire hose is give you an overview of what architecture can be used for. As I said earlier, architecture can often be used as the thing that you tack on your title to make you sound more important. And what I'm trying to show you here is that roughly for the last 20 years, there have been specialists digging into the idea of how do we design systems so that they do what we want them to do, okay? And they've come up with a bunch of cool ideas. They've named the things that they've found. They've analyzed the things that they found such that it's a reusable nugget. So you can say a 3-tier system would be appropriate here, or a pipe and filter system would not be appropriate here. You can just pick up that analysis out of the box. You don't have to wait till you're 50 years old. You can instead learn it declaratively today. I don't want you to think that you should always start out every project with a big upfront 3-month architectural analysis effort. I think on some projects that's completely called for because it's really challenging. On other projects, have less risk. That there are other risks that you're worried about. You may be worried about time to market. You may be worried about there's only 2 of us coding on the weekends, right? There's other reasons why you may choose not to do so much architecture. But I think most of all, at the end of this, there's 2 messages. First, I want you to have a bookmark inside your head that says, when I have problems that look like this, I know to come back and read the literature. I am not an SQL expert. I'm not a database expert. I'm not an expert in a lot of different fields. But I sort of know that those things exist, and if I needed to, I could go read their books. So I want you guys to know that there's a lot of stuff been done by the SEI. The Documenting Software Architectures book is excellent, and you can go pick up those books and learn how to do software architecture. At the very beginning, I mentioned that there was one thing I wanted you to walk out with and say, if you remember nothing from this course, I want you to remember this one thing. Does anyone remember what that one thing was?
Trade-offs.
Trade-offs. Yes, so the trade-offs is the corollary. The basic idea is that for any given functionality, you can choose a lot of different architectures, and then you have to evaluate then the trade-offs, right? But a lot of people seem to think this is the right architecture, right? And it's not a matter of this is the right architecture. It's if you really made me work very hard, I could make almost anything work, okay? But the big deal is if you choose one that's appropriate, a lot of things become easy for you, right? You've sort of automatically chosen the right spot in the design space, okay? So just think about that as you design systems.